Imagine your compass needle spinning wildly over the South Atlantic. It's not broken. Earth's magnetic field is right there. But wait, the title says Pacific? That's a mistake we'll correct. This is the South Atlantic anomaly, a dent where the inner radiation belt dips to just 200 kilometers. The magnetic field is so weak, a compass barely responds. Discovered by Explorer 1 in 1958, this region spans the size of the US. Its field is 30% weaker, a window into Earth's turbulent core. What makes Earth's magnetic shield so uneven? Deep inside, churning molten iron generates our magnetic field, but that shield isn't uniform. Charged particles form two donut-shaped Van Allen belts. Normally high, the inner belt dips to just 200 kilometers over the South Atlantic. That dip creates the anomaly, a 30% weaker field. Satellites passing through get zapped by 1,000 times more radiation. So, what is this patch? It's the South Atlantic anomaly, a region where the magnetic field weakens, spanning the size of the US. The title says Pacific, but it's actually over the South Atlantic. Let's set the record straight. Here, the field is 30% weaker. A compass needle barely responds, deviating by degrees. That's why your compass fails, if you were sailing in the South Atlantic. Discovered in 1958, the anomaly is a sign of deeper turmoil, a patch of reversed magnetic flux at the core mantle boundary, drifting westward at 20 kilometers per year. Satellites passing through get hit by up to 1,000 times more particles. One NASA scientist calls it a pothole in space. The Hubble Space Telescope powers down its instruments during every crossing. As NASA explains, we have to turn off its instruments to avoid damage. Even the ISS takes shelter. An ESA scientist warns, this region is a natural particle accelerator causing electronics failures. But here's the catch. The anomaly isn't static. It's drifting westward at 20 kilometers per year, and recent data shows it's growing and splitting into two lobes. This is a dynamic feature. A patch of reversed magnetic flux at the core mantle boundary pulls field lines inward, weakening the anomaly. As the core churns, this patch expands, stretching and tearing the anomaly apart. By 2020, the anomaly split into two lobes. This suggests a dynamic core, one that could be setting the stage for a geomagnetic reversal. The field has weakened 9% globally in 200 years. The last full reversal was 780,000 years ago. Could this be the beginning? Geomagnetist Dr. John Tarduno says, "We don't know if it's a precursor to a reversal, but it's a fascinating laboratory for studying core dynamics. But it's not just curiosity, it's a threat. Satellites face up to 1,000 times more radiation, forcing power downs. Hubble shuts its cameras every pass. For now, it's a manageable nuisance, a pothole in space, reminding us our planet is alive and changing. On the ground, it's invisible. But for satellites and astronauts, it's a constant threat, a reminder that our magnetic field is a dynamic, living system. That compass failure, it's a glimpse into Earth's core. The same process that spins your needle also protects us from solar radiation. But what exactly causes this reversed flux? Deep in the core, molten iron convects like a lava lamp, generating electric currents that create magnetic field lines. Sometimes these lines get tangled and reversed. Seismologists use earthquake waves to map the core. They've found a region of dense, iron-rich rock at the core mantle boundary beneath Africa, the African Large Low Shear Velocity Province, or LLSVP. This LLSVP acts like a bottleneck. It disrupts the normal flow of molten iron, creating patches of reversed magnetic flux. The South Atlantic anomaly sits right above this region. The anomaly drifts westward at 20 kilometers per year because the outer core rotates slower than the mantle. This drift means the weak spot moves, affecting different satellites over time. Satellites in low Earth orbit, like those in the International Space Station's orbit, pass through the anomaly multiple times a day. The increased radiation can degrade solar panels and corrupt memory. The Hubble Space Telescope avoids the anomaly entirely by powering down its instruments during each crossing. This costs valuable observation time. About 15% of its orbit is lost. The ISS also takes precautions. Astronauts retreat to shielded modules during crossings. The European Space Agency monitors radiation levels in real time to protect crew and equipment. Recent data from the SWARM satellite mission shows the anomaly is not only drifting, but also growing in area and splitting into two distinct lobes. This suggests complex core dynamics. Could this splitting be a sign of an impending pole reversal? During reversals, the field weakens and becomes multipolar. The last reversal took thousands of years, but we are overdue. The global magnetic field has weakened by 9% in the last 200 years. While fluctuations are normal, this rapid decline is unusual and may indicate the start of a reversal. Understanding the anomaly is crucial for space weather forecasting. A weaker field means more cosmic rays reach Earth, affecting airlines, power grids, and even astronauts' health. Scientists use the anomaly to study core dynamics without drilling. By monitoring its changes, they can infer what's happening 3,000 kilometers below, a natural laboratory for geophysics. For now, the anomaly is a manageable nuisance, a pothole in space that forces careful planning. But it's a vivid reminder that our planet is alive, and its magnetic field is ever-changing. But what exactly happens at the core mantle boundary? Seismic waves reveal a massive blob of dense rock beneath Africa, called the African Large Low Shear Velocity Province. This blob disrupts the normal flow of molten iron, creating patches of reversed magnetic flux. This disruption causes localized patches where the magnetic field points opposite to the global field. These reversed flux patches pull field lines inward, weakening the overall field strength above them. The South Atlantic anomaly sits right above one such patch. The anomaly drifts westward at about 20 kilometers per year because the outer core rotates slower than the mantle. This drift means the weak spot moves over time, affecting different satellites and regions. Tracking its movement helps scientists understand core dynamics. The European Space Agency's SWARM satellite mission, launched in 2013, provides high-resolution data on the anomaly. SWARM's 3 satellites measure magnetic field strength and direction, revealing that the anomaly is not only drifting, but also growing and splitting into 2 lobes. By 2020, data showed the anomaly had split into 2 distinct lobes, each with a weaker magnetic field. This splitting suggests complex processes in the core, possibly related to the growth of reversed flux patches. Scientists are watching closely to see if this trend continues. Could this splitting be a sign of an impending pole reversal? During reversals, the magnetic field weakens and becomes multipolar. The last full reversal was 780,000 years ago, and the field has weakened 9% globally in 200 years. Some scientists think we may be overdue. A weaker magnetic field means more cosmic rays and solar particles reach Earth. This can disrupt power grids, affect airline communications, and increase radiation exposure for astronauts. Understanding the anomaly helps us prepare for these space weather threats. So next time you hear about the SAA, remember, it's a call to appreciate the dynamic planet beneath our feet, a planet whose magnetic heart beats in ways we are only beginning to understand. And it's in the South Atlantic, not the Pacific.